So in this lecture today, we are going to find out the integration of the series of a sequence of non-negative measurable function. And then so far we have done integration or Lebesgue integration of non-negative measurable function. Then we are going to transfer the theory in case of general function, means any sort of measurable function, whether it is negative or non-negative. So we are going to do general integral as well as integration of the series of a sequence of non-negative measurable function. Alright, so and then we are also going to see some important example. First, let us have one important theorem about the integration of the series of non-negative measurable function. Okay, so let Fn be a sequence of non-negative measurable functions, and then integration, summation inside integration is exactly equal to summation outside integration of Fn dx. Right, so this is in practical purpose, this is going to be used very useful. All right, so because if you want to find out the integration of a series, then how to find out? First, find out the integration of its term and sum of, okay, general term and sum of. That will give us lots of utility. So yeah, proof. Let us put Sn is equal to the partial sum I running from 1 to n fi. Then Sn are it is a sequence, and since fi are positive, they are non-negative measurable function. We have this one. Sn is a monotonic increasing, means Sn plus 1 will be greater than or equal to Sn. That is, Sn is a sequence of non-negative measurable monotone increasing function. Alright, so then if we put f is equal to the sum of this series, then the sequence Sn is monotonic increasing and it is converging to f. Alright, so we know that integration of the finite sum Sn is exactly equal to this one, and that is, you can take out the summation outside the integration fi dx. So that part we have done for positive functions, measurable positive function. And then by a monotone convergence theorem, what we have is, you can take limit outside of integration, and that is exactly equal to integration limit inside. That is coming from monotone convergence theorem. Alright, so that means limit integration Sn dx is equal to, now what is Sn? Sn is the finite sum, so you can take out this finite summation outside integration. But limit Sn tends to infinity means you can put in this form summation n going from 1 to infinity integration Fn dx, and that is what we wanted to prove. That is, summation n going from 1 to infinity integration Fn dx is exactly equal to integration summation n going from 1 to infinity Fn dx. Alright, so now let us find out some example of strict inequality of fatou's lemma. So we know fatou's lemma. Fatou's lemma is inequality. So that strict inequality happens in some very rare examples. So we are going to find out a very beautiful example in which fatou's lemma's strict inequality holds true. Alright, so give an example where strict inequality occurs in fatou's lemma. Alright, solution: consider the sequence of function Fn defined on x 0 to close on the left and open on the right as follows. Alright, Fn is equal to chi function if n is odd. Alright, so if n is odd, Fn is equal to chi function 0, 1, 2. If n is even, Fn is equal to chi function open interval 1, 2. Alright, since 0, 1 interval and open interval 1, 2, they are measurable. So the chi function is measurable, and this sequence of function is also measurable, and they are non-negative. Okay, so if f twice n minus 1, that is when this one is odd, that is exactly equal to 1, then what we have? If it is odd, then if it is 1, then because of the definition of a characteristic function, f twice n x is equal to 0, and vice versa. If one of the odd function or if one of the function is 1, another function will be 0. If this is 1, then the odd function will be 0, like that. So because why it is happening, because if x belongs to 0 1 closed interval, means that x does not belong to 1 2 interval. If it is here, that is the characteristic function defined on this interval will be 1, that is here. If this x is if x is here, that means x is not here. Okay, so x is here means x is not here, like that. Okay, so let f is equal to limit infimum fn. For this sequence of function, the limit infimum f is equal to limit infimum fn. We put f is equal to limit infimum fn. So therefore then f is equal to 0. The limit infimum is 0 because it is a ultimately sequence of 0 1 points. Alright, so limit infimum will be 0. So let us see why it is limit infimum equal to 0. Explanation: x belongs to 0 1 closed interval means, you know, f1 x is equal to 1. So when x is in the close of this interval, f1 means odd, therefore the characteristic function is defined on this interval, and that is why it is 1. So if x is here, x will not be in the 0 1 2 open interval, therefore even function will be 0. So every odd function will be 1 and every even function will be 0. So you are going to take the infimum of 1 0 1 0, and that is exactly equal to 0. So f of x, the limit infimum is equal to 0 if x is in 0 1 closed interval. Alright, so if x is in 1 2 closed interval, open interval, what happens? Let us see. If it is here, then x will not be in 0 1 closed interval, therefore the characteristic function defined on 0 1 closed interval, that is odd function, will be 0, and even function, the characteristic function defined on 1 2, they are 1. So even are 1 and odd are 0. So in fact, in you are taking infimum of 0 1 0 1, this sequence of 0 1 number, and that is 0. So in this case also the infimum limit infimum function is equal to 0. So in both the situation you have f is equal to 0, that is the limit infimum is equal to 0. Alright, so for any natural number n, we have integration 0 to 2 fn dx is equal to, you can break up 0 to 1 fn plus 1 to 2 fn, that is equal to 1, because if this is not equal to 0, this is going to be 1, then that the integration is 1. So if this is 0, this is going to be 1, and that integration is also 1. So this integration is exactly equal to 1 for any natural number n. Alright, so therefore limit infimum, if you take limit infimum outside, that is exactly equal to 1 because they are all 1. So you have 1 1 1 1, so that for that if you take limit infimum, that is exactly equal to 1. Alright, so therefore limit infimum, the limit infimum taking outside the integration, that is 1, limit infimum taking inside the integration, that is equal to 0. So strict inequality happens in this example, and this is very nice example. Okay, so another example, let us show that integration of this function 1 upon x 1 to infinity is exactly equal to infinity. So far we have developed so many, you know, theory of Lebesgue integration. Using those theory, we are going to, you know, solve some practical example. Let us see. This is one of the typical example how we use Lebesgue theory to find the integration. So let us see. The function 1 upon x is continuous in the interval 1 infinity. Therefore, it is measurable. Every continuous function is measurable. Alright. The function 1 upon x is non-negative measurable function. So it is a non-negative measurable function. Therefore, according to the Lebesgue theory of integration, its integral is defined, and we can find out. Let us see. And 1 infinity, this interval you can write in this form: k going from 2 to infinity, k minus 1 k, a disjoint union of intervals. This is a disjoint union of intervals. This domain of integration can be written in this disjoint union of interval. Alright, so then again we use the theory integration 1 to infinity, you can use in this disjoint union form dx by x, and then this disjoint union you can transfer into summation form, k running from 2 to infinity, integration k minus 1 k dx by x. Okay, so then if you this infinity, you can take limit infinity and tends to infinity in this form. All right, so we know that 1 upon x is strictly greater than 1 upon k in this interval, k minus 1k in this interval. 1 upon x is strictly greater than 1 upon k, so integration of 1 upon x will be greater than integration of 1 upon k. But what is the integration of 1 upon k? That is 1 upon k, exactly. Integration k minus 1 to k dx by k is equal to 1 upon k. So this integration is greater than 1 upon k for every k. Alright, so it follows that this one is equal to limit this one, and this is strictly greater than summation k running from 2 to infinity 1 upon k, because each term is greater than 1 upon k. But this sum is, this sum is divergent, it is infinity, so that is equal to infinity. But this integration is going to be greater than infinity, so what is the only possibility is that this integration itself should be infinity. Okay, so therefore integration 1 to infinity dx by x is exactly equal to infinity. So this is one of the very nice example in which we have used those theory, Lebesgue integration theory, and many results. Okay, so the general integral, as I told you earlier, in this section, what we are going to do is that we are going to extend the theory of Lebesgue integration of non-negative measurable function into negative measurable function also. So how we do that is very interesting and very simple also. Let us see. If fx is any real valued function, okay, then we can define a non-negative measurable function like this. Okay, if f of x may be any function, whether it is negative or non-negative, but f positive you can define as a maximum of f of x and 0. Now f negative you can define as a maximum of minus f of x and 0, and both are non-negative measurable function. It is obvious, because f positive is equal to maximum of f of x and 0. If f of x is negative, that is going to be 0, and then f positive will be 0, that is non-negative. Alright, if f of x is positive, then a maximum of positive number and 0 is that positive number. In that situation is also f positive is non-negative. So likewise f negative is also non-negative. Alright, and they are measurable non-negative function. So the given function f of x can be converted in terms of two parts, f positive, f negative, what are non-negative function. Okay, so let us see. Positive, they are positive and negative parts of f respectively. This is called the positive part and this is called negative part, but both are non-negative measurable function. Alright, so theorem 1, we are going to first prove that f is equal to f positive minus f negative, and the modulus of f is equal to f positive plus f negative, and they are all non-negative function that I have already explained. So this is the tricky part. F is equal to f positive minus f negative. From here we are going to define Lebesgue integration. Okay, the given function f, that may be negative or positive, doesn't matter, but it can be expressed ultimately into the difference of two non-negative measurable function. Okay, let us see. If f is measurable, f is measurable if and only if f positive and f negative are both measurable. This function is measurable, this function is also measurable, then f is measurable. Conversely, if f is measurable, both f positive and f negative are measurable. Number 2, let us prove it. So if f is non-negative, then f positive is equal to maximum of f of x, 0, f of x. If f is non-negative, maximum of these two number will be f of x itself, and f negative, that is equal to maximum of this one and this one will be 0, because if f of x is positive, minus f of x will be negative. Alright, maximum of a negative number and 0 is 0. Alright, so f of x is equal to f of x, you can write in this form, and this part has been converted into f positive and 0 is f negative, and that is equal to f of x. So when f of x is non-negative, this equality is okay. Alright, and modulus of f of x is equal to, you can write, since f of x is positive, this is f of x plus 0, but this part is 0, you can write in this form, so like this. Okay, So if f of x is negative, then f positive x is equal to maximum of this one is 0, and f negative x is equal to maximum of this one is minus f of x. So f of x you can write in this form 0 minus f of x, and but 0 you can write in this form, that is f of x. So again, modulus of f of x is equal to 0 plus minus f of x, you can write in this form, but 0 you can write f positive x, that is like that. So therefore, we can conclude that f of f is equal to f positive difference f negative in both the situation, positive or negative, and modulus of f is also equal to f positive plus f negative. Alright, so it is obvious that f negative is greater than or equal to 0, f positive is greater than or equal to 0. From the definition it is very clear. Okay, so we have done number 1. Now let us do number 2. If f is measurable, then f positive is equal to maximum of f of x 0, and f negative is equal to maximum of minus f of x 0, and they are measurable. That also we have done in the previous theory. So conversely, suppose f positive and f negative are measurable, then f, you can write f in this form, difference of two measurable function, therefore f is measurable. Alright, so if f is measurable function and integration of f positive is finite, likewise integration of f negative is also finite, then what we say that f is integrable, and its integral is given by integration of f, that is exactly equal to integration of f positive minus integration of f negative. Okay, so if the integration of the positive part and negative part are finite, we say that f is integrable. Okay, Lebesgue integral is different from integrable. If the integration is finite, we call it integrable. Whether the integration is finite or not finite doesn't matter, that we call it Lebesgue integral. Okay, so we write the integration of f is equal to in this form when a function is integrable. Okay, from the definition it is clear that f is integrable if and only if f modulus of f is integrable, because if both are finite, their sum is also finite, and their sum is equal to integration of the modulus. Okay, and that is also finite. Alright, so definition, if E is measurable, said f is measurable function. Okay, and chi f is integrable, we say that f is integrable over E. Alright, so and its integral is given by integration over E, f dx is exactly equal to integration f chi E dx. Alright, so definition, another, if f is measurable function such that at least one of the integral f positive of it is finite. If this one is finite or this one is finite, and then what we say that integration of f is exactly equal to integration of f positive minus integration of f negative. Okay, we don't say that it is integrable, but what is the integral of f when one of the function has finite integration? Either f positive has finite integration or f negative has finite integration. In that situation, how we define the integration of the f, okay, is equal to integration of f positive minus integration of f negative. Okay, so let f and g be integrable function, and then number 1, a times f is integrable, and integration of af dx is equal to a times integration f dx. This theory we have already done for non-negative measurable function. We are extending that result to the general function f, okay, and g. So and then sum of the function f plus g is integrable, then integration of sum is exactly equal to sum of the integral. Number 3, if f is equal to 0 almost everywhere, then integration of f dx is equal to 0. And this result also we have done for non-negative measurable function, but now here we are going to do for any general function f. So number 4, if f is less than g almost everywhere, then integration of f dx is less than or equal to integration g dx. Okay. Number 5, if f and v are disjoint measurable set, then so integration f over the union a union b is equal to integration a f dx plus integration b dx. Alright. Suppose a is greater than or equal to 0, then af positive, that is equal to a f positive, and af negative is equal to a times f negative. Okay, so integration is equal to this, since it is a positive part, you can take out, this is non-negative measurable function. Therefore, for that we have already done that the multiplier a can be taken out of the integration, and since this is finite, integration by another a positive number, that is also finite, and integration a f this one, that is also same thing like this. Okay, so f is integrable. AF is integrable by definition, and therefore integral of AF is equal to the positive part difference the negative part, but that is exactly equal to a times integration f dx. Okay, suppose a is equal to -1, then -1 f positive part is equal to f negative, and minus f negative part is equal to f positive. So integration minus f positive part is exactly equal to integration f negative part, and this one is equal to this one. All right, so integration minus f dx is equal to positive part difference negative part, but this positive part is negative part and this negative part is positive part. So this you can write like this. Okay, if a is negative, then you can write a is equal to -1 times modulus of a. So af is equal to minus of, and this is positive number f. All right, so for this one just now we have done, and it follows that af dx is equal to minus a this one, but this minus you can take out outside the integration. Again, this is positive, you can take out outside, and that is exactly equal to a integration f dx. All right, so hence integration af dx is equal to a times integration f dx. Okay, number 2, we know that the positive part of the sum is less than equal to sum of the positive part, and similarly negative part of the sum is less than equal to sum of the negative part, like that. So integration of this one will be less than equal to sum of the integral of this one, and they are finite, therefore this is finite. Similarly this one is also finite, therefore f plus g is integrable. Okay, so f plus g is integrable. And then what is f plus g? You can write in this form: positive part of f plus g and minus negative part of f plus g, and that is, after simplification you can write like this, and you can simplify further like this. All right, so in this situation all are non-negative measurable function, therefore the theory you can apply here. Okay, so this equality, and then after simplification you will get this one. So that is exactly equal to integration f dx plus integration g dx is equal to integral of f plus g. All right, so number 3, if f is equal to 0 almost everywhere, then f positive is equal to 0 almost everywhere, and f negative is also 0 almost everywhere. Okay, that is pretty simple. And so integration of f positive, since non-negative measurable function, that is almost 0 almost everywhere, therefore its integral is 0, that we have done so many times. Similarly this is also 0, so therefore integration of f is equal to difference of the integral. All right, that is 0 minus 0 is 0. So number 4, we can write g in this form: g is equal to f plus g minus f. Since g is greater than or equal to f, this is non-negative, so you are adding to f a non-negative term like this. Okay, so therefore what we have, since g is greater than or equal to f almost everywhere, you can assume that g minus f negative part is 0 almost everywhere. It follows that by the previous result number 3, integral of g minus f is equal to 0. All right, so then you can write integration of g in this form: integration f plus g minus f. So then you can break up using the previous result: integration f dx plus integration g minus f dx. All right, but this is non-negative. Okay, so that is exactly equal to integration f dx plus integration g minus f positive part minus integration g minus f negative part. Okay, but this part is 0, we have shown that one. So therefore this sum will be greater than this one. All right, because this part is 0 but this part is non-negative. Okay, so you are adding to this a non-negative number, therefore that will be greater than integration of f dx. All right, so therefore but what is this? And that is exactly integration of g dx. so that is greater than or equal to integration of f dx. Okay. Number 4, since a and b are disjoint sets, we can write characteristic function a union b exactly equal to sum of the characteristic function a b. All right. So therefore, if you multiply both sides by f, you have this one, and then if you integrate both sides, you have this one. All right. So that is integration, but this one you can write integration over a union b, this one over a, this one over b. So yes, this completes the proof.